Welcome to our engineering numerical analysis presentation, Trajectory of Satellites in Orbit. We are Group 12 and our members consist of Eunjun, Sunwoo, Kristen, Yongjun, and we are going to solve the trajectory equation based on restricted two-body motion.
We are using Kepler's equation as our governing equation. Kepler's equation represents the relationship between time and angular displacement. Our goal is to draw a trajectory of a satellite by solving Kepler's equation under following assumptions. The mass of satellite is negligible to Earth. The coordinate system is inertial. The satellite and Earth can be treated as a point mass. All forces besides gravity are negligible.
We first want to convert an Earth fixed coordinate system to an inertial coordinate system. We do this through a series of geometric transformations detailed in the coming slides. Then we want to use two different independent numerical approaches to reach the final solution. First, by manipulating Kepler's equation, we can get it into a nonlinear form where we can apply root finding methods to determine the solution. Second, by defining a governing equation for the orbit through a second-order differential equation and solving that with an IVP method. For this project, we primarily chose to focus on Chapter 3 of our course, solving nonlinear equations by comparing three such methods: bisection root, regula falsi, and Newton-Raphson. We compare these three methods to MATLAB's built-in function ODE45, which solves an IVP.
First, we set initial values for position and velocity. For the rest of the video, we may be referring to these metrics as R and V vectors. We can select any values near orbital velocity, but setting relatively close initial values to the true solution is quite important for open root finding methods, such as the Newton-Raphson method and IVP methods. The R and V vectors we choose are directly taken from an astrophysics textbook, and as we explain later in the presentation, our root finding methods took a relatively short number of iterations to converge to the solution, proving that these initial values are a good starting point.
Second, we need to convert R and V vector into classical orbital elements, or COE for short, include the following: eccentricity, semi-major axis, inclination, right ascension of ascending node, argument of periapsis, and true anomaly. COE are the 6 elements needed to specify the position and motion of a satellite. The eccentricity and semi-major axis determines the shape and size of the orbit, respectively. The inclination determines the angle between the plane of orbit and the inertial reference plane. The right ascension of ascending node, or RAAN, determines the angle between the inertial I-axis and the direction of the ascending node. The argument of periapsis is the angle between the ascending node and the periapsis, the closest point of orbit from the focus. Finally, the true anomaly is defined as a transformation of the true angle pointing towards the satellite, determining its position. Here we show a screenshot of the geometric formulas we use in our code, taken from an astrophysics textbook.
The first method we would like to explore are nonlinear root finding methods that we learned from Chapter 3 of this course. Our main goal is to draw a trajectory of satellite orbit, and in order to do so, we must solve Kepler's equation as shown above. We can manipulate this equation and move around the variables so that m equals 0, putting it into a form that allows us to use the following root-solving methods. For each method, we created our own user-defined functions that take in a set number of inputs but gives us the same type of solution. We will be comparing the number of iterations and graphing the solutions to determine which method is most efficient.
Before graphing, we must convert our COE variables back into R and V vectors. These vectors contain position and velocity values that correspond to each value of our time domain. Finally, the code plots the result. Here we show a comparison of all three COE, or nonlinear root finding methods. We notice that these methods are incredibly similar, which is to be expected. However, the biggest difference we see is that closed bracket methods have a much longer computation time because they require more iterations to get to the solution. These are the outputs from our user-defined functions. We notice that they are all converge to similar solutions, but that Newton-Raphson is the most efficient.
This is a graphical comparison of solutions using IVP versus the COE methods previously described. We use the ODE405 MATLAB built-in function to solve the IVP. We chose to plot the Newton-Raphson method against the IVP method because of its efficiency and similarity compared to the other nonlinear root finding methods. Here we can see that these two methods are also very similar to each other. And because we want to test these methods with more realistic situations, we also want to compare the two methods over an increased period.
This leads us to the graph on the right, which shows much more different results than previously shown. The two methods are the exact same, but in this situation, we have increased our period to 30 times what we originally plotted. As you can see, the ODE method continues to converges towards the center, diverges away from the solution, which is odd behavior. The ODE method has a gradual increase in truncation error, therefore deviating from the solution as you increase the period. The behavior we don't want to see, however, is shown with the Newton-Raphson method. We can see a consistent elliptical pattern despite this large increase in period.
To conclude, let's summarize what we learned. Through these graphical representations and outputs, we noticed that firstly, all nonlinear solving methods have similar results with a duration of 1 period. Closed bracket methods, namely bisection and regula falsi methods, are quite accurate and always converge to the solution, but require lots of computational space and time to execute. Therefore, we chose to compare the IVP method to the open, nonlinear root finding method, specifically Newton-Raphson. For 1 period, the two methods are practically identical, which proves our methodology to work as we wanted it to. However, to simulate a more accurate satellite orbit, we increased the period number to see how it influences our graphs. Quite obviously, the IVP turns into an inaccurate method as it diverges further and further away from the solution, whereas the COE method stays consistent despite the drastic increase in period. We can conclude that the IVP method is not ideal for larger domains and bigger sets of data because the truncation error accumulates. Therefore, we believe the Newton-Raphson method to be the most efficient and accurate for purposes of this satellite orbit model. These are our member roles, and thank you for listening to our presentation.